It's the final countdown. Ba-da-ba-ba. Ba-da-ba-ba-ba. Ba-da-ba-ba. Ba-da-ba-ba-ba. That's right, folks. With Unit 10, we finally enter the home stretch. It's the beginning of the end. It's our final unit of Algebra 1. Okay, now we've spent all of our time thus far building a really strong algebraic foundation. We know how to graph lines and parabolas, solve equations and inequalities, simplify radicals and exponents, and much, much more. Doing all that practice serves a purpose in and of itself, but it's also part of a larger picture. Behind the scenes, everything we've been doing has secretly prepared us to understand these things in math that we call functions. Hence the title of our lesson today, Class 10.1. Let's talk a little about some function basics. To kick us off, when introducing the concept of functions, I often like to ask, well, what does it mean for something to function? So take a couple seconds, pause the video. When you hear the word function, what comes to mind for you? No right answers, just curious where your brain goes. What do you think? Alrighty. Well, if something is functioning, that means it's doing something. If I interpret that slightly differently, well, maybe I could say that it's working or that it's operating somehow. But there's an added layer to the word function that I think is really important here. If I'm doing my function, or if something is doing its function, it's not just doing stuff willy-nilly. There's an added layer of expectation to the things that are happening here. So we're doing or working or operating as expected. Things don't happen randomly, right? We're serving some kind of purpose or fulfilling some kind of role, or there's some rule that we're following that's telling us how we can expect things to behave. With this in mind now, I want to understand how a mathematical function functions, pun intended. One way to do so is actually by turning our attention back to graphing, and specifically the process of finding points on a graph. Say I have this linear equation, y equals negative 4x plus 7. It's a line, so I want to find 3 points, 3 ordered pairs on this graph. So what's the strategy that I might use to find these points? And as I do, there are 2 things that I want us to notice. Be thinking about things that I might say are kind of valuable to us as we go through this process. Either way, let's get pointy. Go ahead. Alrighty. Well, if I want to find some points, just like quadratics, one strategy that I know would be to plug in some values of x and see what values of y I get. Now I can choose any values of x that I want. I'm going to choose -1, 0, and +1 so that I get some variety, something negative, something positive, and something 0. Now if x equals -1, to find the value of y, all I need to do is evaluate, which is just a fancy word for substitute in. So I've got -4 times -1 plus 7, which would be 4 plus 7. This gives me the y value of 11. Same thing for x equals 0. Here, y is going to be equal to -4 times 0 plus 7. Using my order of operations, this would become 0 plus 7, which gives me a y value of 7. And for 1 here, y is going to be equal to -4 times 1 plus 7. -4 times 1 is -4. Add 7, and we get a y value of 3. But again, these are points on my graph, so if I express these as ordered pairs, I know that the points -1, 11, 0, 7, which should be my y-intercept, and 1, 3 will populate the graph of my line. Cool. Now, as I identified these ordered pairs, there are 2 things that I hope you might have noticed. First of all, the values of y that we get, they don't come out of nowhere. We get the y values of our points from the values of x that we plugged in. And second of all, when we plugged in those values of x, notice that -1 only gave me 11, 0 only gave me 7, 1 only gave me 3. For any value of x that I would plug in, it's going to get me exactly 1 value of y. listing both of these things out, I hope that makes it clear that there is some kind of relationship, and in fact, not just any relationship, but a dependency between our variables x and y. When I take those values of x that I plug in, so I can think of these guys like input values, by following the rule, negative 4x plus 7, I get these output values of 11, 3, and 7. Lovely. So with all of this in mind, that idea of dependency between input values and output values forms the basis of what we call in math a relation. Now, a relation is just a rule or some kind of map that establishes a relationship between two sets or collections of values. Of these, we're specifically interested in a special type of relation called a function. And a function just takes every input value to exactly one output value. There are lots of ways to think of functions. One way that I like to think of a function is like a vending machine. So say, for example, that in the vending machine that's poorly drawn off here to the bottom left, I want to get a blue circle snack. Now, my blue circle snack can come from a number of different inputs, right? So I could plug in 1, I could plug in 2, or I could plug in 9, and I would still get my circle snack. That actually has nothing to do with being a function. The important thing is no matter how many times an output value shows up, if I input something, so here I press 1 on my keypad, that input 1, I can always expect to reliably get me the output value of that circle snack that I want, right? So this is what makes a function. It doesn't matter how many times an output appears, as long as the input always gets me only one output, then I have a function. Now, for any function or relation, there are specific words that we use to describe those inputs and outputs, and we actually borrow some terminology from our graphing. Domain, we formerly used to represent values of x. Here, domain, if we think of the x as our inputs, this is going to give me the set of all of my input values, usually represented by the variable x. And our range here, rather than thinking of it as values of y, the range is going to be the set of all of my possible outputs, which we typically connect to the variable y. Beautiful. Now, functions can also be visualized. They don't have to be just abstract. One way to visualize what a relation or a function does is by using this tool called a mapping diagram. So I have these collections here indicated by these ovals of values, or in this case, just of some numbers or some stuff. And I can use my rule to determine where each of those inputs is going to go. For the one on the left, my rule is I'm going to take each of my diets, carnivore, herbivore, and omnivore, and map it to the things that each of those diets would eat. So carnivores eat meat. So in my mapping diagram, I would draw an arrow from the input of carnivore, so here's my domain, to the output of meat in my range. My herbivores, of course, they only eat plants, so they're getting an arrow there, but omnivores eat both meat and plants, so I'm going to get an arrow from my input omnivore to both of those outputs. Now, is this a function, right? By definition, a function can only take an input to one output. Well, if I look at omnivore, right, I have an arrow going to meat and an arrow going to plants. Here, this input goes to two different outputs. So in this mapping diagram, I can see that no, this is absolutely not a function. But on the right, if I take this guy, I have each of my numbers being mapped to the number of letters in its name. Well, if I were to spell out 0, that would have 4 letters. 1 has 3 letters. 2 has 3 letters. 3 has 5, 4 has 4, 5 has 4, and 6 has 3. Now you'll notice, right, this guy in the domain on the left, each of those inputs went to exactly one friend in our set of outputs, our range. So this does meet our criteria. This guy absolutely is a function. Beautiful. Now we can represent functions in words like this, but we also are often interested in representing our functions algebraically. To write those function rules algebraically, we typically use what's called function notation. And now function notation, in essence, is just a fancy way to say that I'm taking my variable y and I'm going to replace it with the following symbol. We call this f of x. Sometimes we might use g or h, but here, right, that can continue on and on, but this just is a way for us to make the dependence on that input x more obvious. Taking my rule from above, y is equal to negative 4x plus 7, all I would do is swap y for f of x. So my function would be f of x is equal to negative 4x plus 7. Right, I can also, if I so choose, represent this in words, even though here there's an algebraic rule that I'm following, right? What is this function really telling me to do to the input value x? Take 30 seconds. What am I doing with x here by following this rule? Go. Okay, well, in words, if I follow this rule, the first thing that I'm going to do is multiply my input value by negative 4. And after I multiply by negative 4, all I'm going to do is add 7. So I can verbalize here what this function is telling me to do, how it assigns input values to output values. The only question here, right, is like, why would I even bother using that function notation in the first place? How is f of x different from y? Well, as we said before, the reason why we would make this choice is because it's going to make the dependency of that relation clear. So f of x, this guy here, it depends on that value of x. So we say that f of x here is going to serve as our dependent variable. Its value depends on the value of x that we plug in, but x can be whatever it wants. It has no dependence, so we are going to call this guy our independent variable, right? Ooh, I can spell. Independent variable. So this guy here, I can plug in anything that I want for x in this case, and then depending on the value of x, that informs my value of f of x, which is really just y. The last thing that I need to know is, well, how do I go about evaluating a function? So say that I have the function rule, f of x equals x minus 3 all over 2. I want to find f of 5. So my input is going to be 5. I want to determine what its output value would be. Well, take a couple seconds, take a risk, take a chance. How do you think I might use this notation to my advantage to find what f of 5 is? Try it out. Alrighty. Well, if I want to find f of 5, again, this guy x here is just our input. So what I'm inputting into the function for x is 5. So 5 is going to take the place of x, which is my input. So I have 5 minus 3 all over 2. Simplifying this fraction now, that's easy. I've got 2 over 2, which simplifies to 1. So I can take this guy and in function notation say a couple of things with it. One way that I can say that the input value of 5 gives me the output value of 1, I could say that f of 5 is 1. So this is one way to state this. I could also say something like the value of my function f at the input value of 5 is 1. And then the last way that I might say this, if I use that language of assigning, I could say that f assigns, or you could even say maps here if you want, 5 in my input set to 1 in my output set. Let's say that I want to find the values of f of negative 6, f of 0, and f of 13 using that same rule above. Try your hand. Alrighty. Well, if f of negative 6 is the thing that I want to evaluate, all I need to do is take that negative 6. It's going to take the place of x. So I've got negative 6 minus 3 all over 2. Negative 6 minus 3 is negative 9 halves, which I might write as negative 9 halves by pulling that minus out in front. Either way, totally fine to leave it as an improper fraction. I have f of 0. So f of 0 is going to be equal to 0 minus 3 over 2. Again, 0 is taking the place of x. So I've got 0 minus 3, which is negative 3 over 2. Again, if I want to be annoying, I might write this as negative 3 halves, but that's totally fine. And f of 13 is my last one. Again, all I'm doing is substituting 13 for x. So this is going to become 13 minus 3 over 2. 13 minus 3 is 10. And 10 divided by 2 is 5. Very nice. Let's try one last one for the road, and then I'll set you free. So we've got g of x is equal to 1 minus x squared. Here's a quadratic function. I want to find the values of g of negative 1, g of 0, and g of 7. Have at it. Okay, so I've got g of negative 1. Again, my strategy is just to substitute. So every time I see x here, I'm going to replace it with negative 1. So I've got 1 minus negative 1 squared. Negative 1 squared is 1, and 1 minus 1 is 0. So g of negative 1 is equal to 0. G of 0, I'm going to substitute again. Every time that I see x, I'm replacing it with 0. So I've got 1 minus 0 squared. 0 squared is 0, and 1 minus 0 is 1. Last but not least, let's try it with g of 7. Again, g of 7 here, I'm going to take 1 minus x squared. I replace my x with a 7. So I've got 1 minus 7 squared, which would be 1 minus 49. And 1 minus 49 is negative 48.